Hello. I'm sorry we didn't have class today. Or maybe you're a future student of mine and you're watching this video on a day we did have class. Either way, these are the things we're going to try to address today, and if we don't get through that all the way, we will do so in later sessions. So first, let's talk about the meaning of the notation in probability definitions. Specifically, come over here, you screen. When you say the probability of some event called E happening, we're using notation to describe the probability, that's the P, of some event, E. It doesn't really matter what letter you put in the inside, but typically we'll use P on the outside. And a lot of notation uses a lowercase p. I think over here they use an uppercase P. It doesn't really matter. P is for probability. There's ways that we can mathematically talk about probability of an event. Your probability will always be some number that is between 0 and 1. This is fancy notation saying that the probability of your event must be less than 1, or equal, could be equal, or and greater than 0, and it could be equal. So once again, the probability of this event must be greater than or equal to 1. Oh my gosh, must be less than or equal to 1 and greater than or equal to 0. Fancy talk for it's between 0 and 1. It could be 0 or 1. All right, other things that you'll do in probability is you'll sometimes see the probability of A is an event and the probability of B is an event. And we want to know, given some certain assumptions we'll talk about more later, what is the probability of them happening at the same time? And you'll see this notated as the probability of A and B happening at the same time. You might also see, if you have probability of two events A and B, what is the probability of A or B happening? Either one of them can happen. And what's the probability that either of them will happen? That's what or means in this mathematical context. In the world, often when we say or, we might be talking about a different kind of logical or. We say, do you want burgers or chicken nuggets to your little kids? Typically, you don't mean both. Typically, you mean one or the other. In math land, that's called an exclusive or, sometimes written as XOR. That's one or the other. In this case, mathematical or means either of them. So anywhere where A or B is happening, either of them, inclusive or. And then there's a couple of mathematical operations we can take on these. Just in case you're interested in the more fancy notation, this can also be written as the probability of A and B. That little arch means and in logical operators. Or the probability of A or B. That little smiley U shape means or in logical operators. So there's some notation there. Typically, we write probabilities as a decimal between 0 and 1. It would be appropriate to write it as a percent. So say our probability of event A was 0.5. We could also write this as 50%. For the most part, this is the kind of notation people use just by convention. Neither one's more correct, but this one's more popular. So you'll probably see it that way on your assignments. You could also write it as 1 out of 2, and in some cases that might actually make more sense if you're choosing one thing out of 2 total choices. Another thing that we might see, let's give probability of B, event B a value. Let's call this 0.2. The probability of 2 events occurring, assuming those events are independent, meaning A or B happening does not influence each other, is the probability of A and B, I'm going to write and B happening at the same time, is in fact the probability of A times the probability of B. And we'll write that out separately just so we can be super clear, like this. And so to find the probability of both of these events happening at the same time, then we would just multiply these probabilities together. So that would be, I'm going to move this over so we have a little more room. Oh, I can just move my whole screen. Digital's so cool. In this case, that would be 0.5 multiplied by 0.2. I'm going to put those in parentheses so the decimals don't confuse us. And if we take 0.5 or 1/2 and we split it into 1/5, then we're going to get 1/10. There's lots of ways to figure out how that happens, but the probability of them happening at the same time is 1/10. This is pretty simple, I think, to talk about them happening together, assuming the events are independent. But it gets a little trickier when you start talking about events that could happen at the same time. The probability of A or B, so either one of them can happen, is going to be a little bit different, and it depends on the situation. That is actually what this fancy gobbledygook right here is trying to communicate. So let's draw some pictures and kind of get an idea. Before that, we need to talk about this idea of mutually exclusive. So let's talk about what that means, what that looks like, and why it's important when we're talking about the probability of one or the other thing happening, which in mathematics means both of them at the same time, and why this works this way. So we'll change to green, make a little line here. So if I have an event A and another event B, then let's say the entire sample space, that's math fancy talk for all the things that could possibly happen, is expressed by this rectangle. And let's say that A can happen anywhere here, and B can happen anywhere here. In a situation like this, there's also a third option where neither A nor B is happening. That's kind of in this empty blank space here. That could happen. We could have, let's say we pick a spot here, so that's just A. We could have just B, but there is no place where A and B happen at the same time, kind of graphically speaking. This is a situation called mutually exclusive. Mutually exclusive. A is mutually exclusive from B, meaning they can't happen at the same time. And mathematically, what that means is interesting in the case of our probabilities. So let's give some real world situations like this. Let's say I can have pickles or I can have apples. I can't have both. Those events are mutually exclusive. I get to pick one or the other. This is the real world or, not the mathematical or. Mathematically, or would mean I get them both. So let's make that clear. And let's say A is our pickles because they're green, and I don't know why our apples are sky blue, but they are, okay? They just are. I can't do them at the same time. That would mean that the probability of A and, sorry, I'll write a and B happening at the same time has to be 0. They can't happen at the same time. They are mutually exclusive. Even if we assign a value of, say, 0.3 for our pickles, about 3 out of 10 times we get pickles, and about 4 out of 10 times we get apples, you might think from up here that we just multiply these together to find the probability of them occurring at the same time. That would be true if they were not mutually exclusive. These cannot happen at the same time. So because they're mutually exclusive, the probability of them happening at the same time is 0. However, mathematically, the probability of them, either of them happening, A or B, in any place, would look like if we shaded in B and A and then added those pieces together. So we have, in mutually exclusive cases, this is probability of A plus the probability of B, and we can walk away happy and we're done. That's great. If we know that they're mutually exclusive, we can just kind of add them up, and now we know that either this or this is likely to happen in the sum of the two probabilities. Easy. Now here's the problem. what if we take our nice little sample space here, and A and B are not mutually exclusive. I'll use some different colors. So this time A is going to sit kind of over here, and B is going to sit like this. And there's a place where A and B can happen at the same time, but it's not in every place. These are no longer mutually exclusive. So let's give these numbers just so we can talk about it. Let's say P of A is 0.2, and P of B is much bigger, much more likely. We'll call that 0.7. And notice there are some places where neither of them happen. That's in our sample space. The sample space is all of the possible outcomes. So it's possible that neither of those things can happen given the way we've drawn this Venn diagram. If you didn't know, Venn diagram is a fancy word for these two circles that are representing one thing that can happen, another thing that can happen, and then when they might happen together. So mathematically, if our probabilities are not mutually exclusive, in other words, they can happen at the same time, that little space right there, then the probability of A or B is, just like before, the probability of A plus the probability of B, and maybe I should write these in the right colors, plus the probability of B. So we have kind of this whole space here for probability of B, and this whole space here for the probability of A. Did you notice that I double shaded a spot? We double counted that middle place. So we actually need to subtract the place where they're happening at the same time. And maybe I'll make it pink just so we can be super clear. That's right here where that's happening at the same time. So we've double counted that. And how do we look at a situation where both are happening at the same time? Mathematically, that's the probability of A and B happening at the same time. So it's the same situation, except for when they overlap, we have to subtract off the extra time that we counted the middle. And that's what this big giant gobbledygook thing up here is trying to tell us, that when we have two events that are not mutually exclusive, then we find their probability of either of them happening by adding them up and then subtracting the place where they overlap. Okay, and then there's this idea of mutually exclusive events in an entire sample space. I really like using those Venn diagrams. I think it makes the concepts clear. Mathematically, we might talk about it a little differently than geometrically or with the Venn diagrams. But let's give an example again, looking at this whole space. These events are not mutually exclusive because the probability of A and B, and I'll write it in that light pink color so it matches the picture, and B is in fact probability of A times the probability of B, or in this case, 0.14. We know that this is not mutually exclusive because there is a chance that they happen at the same time. Whereas we know that these two were mutually exclusive because there is no chance that they will happen at the same time. Okay, so there's one more thing that could happen. We could say the probability of not A, that'd be kind of the opposite of A. And in our diagram up here, I'm going to use a different color to represent this. The probability of not A would be anywhere where A isn't. So that would be kind of all around it, all through B, and in this other space all the way through. And we can look at it like that. And then the probability of not B would be the same thing, except for every space where B isn't. Mathematically, the probability of not A has to be 0.8 because the probability of A is 0.2. Likewise, the probability of not B is 0.3 because the probability of B is 0.7. And the only possibilities here are you are B or you are not. So that has to add up to 1. 100% of the time it's going to be either B or it isn't, right? So those are how those work out. And so in a case where things are mutually exclusive and they take up the entire sample space, let's draw an example of that. Let's say our sample space is represented by this rectangle, and then A is everything from here to here, all of it. I know my scribbles aren't exactly perfect, but let's say this is A. Event A is 0.5 likely to happen, or 50% of the time. And B takes up all the rest of the space. There is no space where A and B are not happening, or A or B is not happening. So B can happen 0.5% of the time, or half the time. And we know that the probability of not A is in fact the same as the probability of B in this case. These events are also mutually exclusive. There is no place where A and B is happening at the same time. So once again, mathematically, the probability of A and B is 0. The probability of A or B is in fact 1. 100% of the time, you're going to get one or the other. There is no opportunity for neither of those to happen. So this mathematically, because A and B is 0, that is mutually exclusive. They can't happen at the same time. And then mathematically, the probability of A or B being 1 means that there are no other combinations in that sample space. The sample space is kind of all the things that could possibly happen in this black rectangle here. We're saying that because the probability of A or B is 1, then that fills all the space. So that's kind of our objective up here. Explain why two mutually exclusive events do not or do cover the entire sample space. And kind of looking at this again, we have mutually exclusive events that cover the entire sample space, and this mathematically is what must happen if that is going on. If we have two mutually exclusive events that do not cover the entire sample space, then we can add their probabilities. The probability of A or B is just their sum, and it's not 100% likely. There's still other options besides A and B. There's neither of them could happen. So mathematically, if A or B adds to 1 or 100% probability, like it did down here, then we're looking at mutually exclusive events, possibly, that cover the entire sample space. Whereas if A or B is not 1, then there are other choices and it does not cover the entire sample space. I think that's enough information to kind of dig in to these problems. I'm going to do a few of them with you rather rapidly because this video is already 20 minutes long and I don't want it to be much longer. So let's talk about selected at random. This is actually really important, number 1 here. When we say selected at random in probability questions, what we really mean is that all events are equally likely. So that means that we could we stick our hand into a bag of marbles and we are equally likely to pick any of the marbles in that bag. In real life, that's probably not exactly true. In fact, when I do drawings with raffle tickets, I will fold and crinkle my raffle ticket and then unfold it before putting it in because it makes your ticket slightly more likely to be drawn. Cool trick, right? So selected at random, we really care because we're saying that every outcome is equally likely, at least in the first event. This notation we've already talked about above. We don't need to hit that again. Let's talk about the probability of picking a black jelly bean. What is that? Licorice, maybe? Sounds good. 5-pound bag. What do we need to know? Okay, there's a lot of ways to answer this question. We could say how many black jelly beans are in the bag. That would tell us. Versus how many total jelly beans. There's other ways to answer this question. You could say, what is the distribution of jelly beans? Are they roughly equal? And how many jelly beans are there in a 5-pound bag? If we knew the total amount of jelly beans, let's say there's 1,700 jelly beans in a 5-pound bag. I have no idea. I'm just guessing. That's probably pretty close though, because I know there's about 2,000 Skittles in a 5-pound bag of Skittles. Anyway, let's say we know there's 1,700 total, and there's 20 different kinds of jelly beans, and they're all equally likely to occur. Then the probability of picking a black jelly bean would be what happens if we take our 1,700, split it into 20 pieces. I don't know what the heck that number is. Let's find my mouse here. That would mean there's roughly 85 of each jelly bean. And if there's 85 of each jelly bean in our enormous bag, then that would mean that 85 out of 1,700 jelly beans are likely to be black. So this is kind of working with probabilities. You could label this. The probability of picking a black is 85 out of 1,700, given these assumptions. I won't answer the question directly, but hopefully that gave you some context for how you might. Oh, okay. Suppose there's 400 jelly beans per pound. I think you can do this stuff. I don't think I need to go through this because we just talked about exactly how we might do that. Yes. And by the way, the answer to this is not necessarily. It depends on the assumptions you make. Okay, so there's 3 outcomes in chess. You can kind of draw a sample space. Win, lose, or draw. Win, lose, or draw being kind of the outside space. Are they mutually exclusive? Can you win and lose? No. So win and lose are mutually exclusive. Are draw and win complementary? We didn't talk about the definition of this, but we did talk about what it means. If I were to say the probability of not B, not D, in our sample space that looks like this, the probability of not D is everything where D doesn't happen. That would mean that D and not D are complements. They add to 1. There's a 100% chance of D or not D happening. So are the events draw or win complementary events? In other words, if you take win and you say combined with D, draw, does that include the entire sample space? The answer is no, they're not complementary events because there's also a probability that you could lose. So win and draw are not going to add to the total because that doesn't account for losing. Okay, using words, what do we mean by the probability of win plus the probability of loss plus the probability of draw? Well, this is the probability that any one of those 3 events happens. You're going to get 1, right? And then why does it have to be 1? We talked about this. Okay. Wow, this is a contrived, awesome math problem. Let's talk about it. What are we at? 22 minutes? Yeah, we have time for both of these, and then we'll call it quits. Suppose the probability of remembering to bring your phone to class is 0.7, and the probability of remembering to bring your calculator is 0.75, and bringing them both is 0.55. So I'm going to draw a picture. It helps me to visualize this. We know that both is an and situation, this and the other. So there's kind of a place, let's do 0.7 for bring your phone and make it blue. So that would be approximately 70% of the total space. I think that's sort of close. And then calculator is 0.75, so a little bit more likely, slightly bigger. And the probability of both of them is 0.55 when this is happening together. So the space right here is where they happen together. How do you find the probability that you will not bring either? Oh, wait, I didn't say that right. How to find the probability that you'll remember to bring either your phone or your calculator? So this is not a mathematical or, unless we are talking in math class. Usually, when we say or in mathematics, we're talking about this could happen or this could happen. That would be an or situation. And when we talk about it in real world cases, we probably mean one or the other. So right here, we're going to assume, once again, this is the assuming language, assuming P of A or, well, can we use P of P for phone? Whatever, we'll use A. or B means mathematical or, and we're not talking about the exclusive or that we talked about earlier. Assuming that is what we really mean, one or the other, either of them, then we have to find a way to add up this space and this space. And you'll notice once again that we've double colored the middle space. And so the way that we do this is using what we talked about over here. If I can get back there. There we are. Where we are accounting for the fact that we've counted that middle part twice. So we subtract one instance of it from the total. So we'll add A and B and then subtract that middle part, which you can do the math for. If the probability of having serial, okay, this is the same kind of thing, and I will not do this problem because I want to see how you do it on your own. I think that is where we will end for B2 today.